In this lecture, we're going to discuss groundwater. So we looked at freshwater's, running water, at least running water's role in the hydrosphere. We're discussing running water. Now we're going to look at groundwater's relative role in the hydrosphere. So we know that 97% of the water on Earth is in the ocean, in salt water, and the rest is not found in the ocean. And of the water not in the ocean, the fresh water, we have those parts listed here: ice sheets, glaciers, groundwater, lakes and reservoirs, soil moisture, water vapor in the atmosphere, and river water. And you'll see the majority of fresh water on the Earth is frozen as ice sheets and glaciers. Okay, that is almost 85% of the total volume of fresh water. However, if you look at liquid water, or at least non-frozen water, groundwater at 4 million cubic kilometers is 14% of the total fresh water on the planet. And if you ignore the ice sheets and glaciers, groundwater makes up 94% of fresh water on the planet. So groundwater is the largest source of readily accessible fresh water on the planet, which makes it a critical resource. So groundwater, though it's out of sight, sometimes out of mind, but it's more important than you may think. So what do we use groundwater for? Well, this pie chart right here is the US daily freshwater consumption. So it's 270 billion gallons per day. 77% of that is surface water, so running water from reservoirs and rivers and streams. Right? So the majority of our water consumption is surface water, running water. However, 23%, or almost 80 billion gallons a day, is groundwater. But what makes groundwater so important is what we use it for. You see that we use the majority of the groundwater for irrigation. And what does that mean? We use it to grow our crops. So whenever you go to the grocery store and you see all the produce, all the fruits and vegetables, and even the grains, the rice, and so forth, that food was grown mostly using groundwater. So if it wasn't for groundwater, we wouldn't have the water necessary to grow all that food. So it's extremely critical. We use about 19% for public supplies. That's towns that use groundwater for the municipal water. About 4% is for domestic use. That's individual households having groundwater through wells and springs. Then we have industrial use, livestock, aquaculture, mining, and thermoelectric. So basically what we use groundwater for is growing our food and for water supplies. Okay, so 68 plus almost 20, so that's like 88, plus another 4, we have like 92% of groundwater is used for either drinking or irrigation. So if we look at this link, this is Rhode Island's water supply. So the beigeish, I guess I should say like the peach color, that is exclusively surface water. So these towns, they're public. Let me start again. So any region that has a color that's not white is a municipal water supply. That means that the water is supplied by the municipality, the town, or the city. If it's a peach color, the water supply is strictly surface water. So, and we have the name. So here's Providence Water Supply Board. Then we have Johnston Water, Greenville Water District, Smithfield Water Supply Board, Lincoln Water, East Smithfield, and East Providence Water. So where they get their water from in this peach region is the Scituate Reservoir. And so we also have surface water down here in Portsmouth, Aquidneck Island, and lower parts of Jamestown, and northern parts of Tiverton. And there's a reservoir on Aquidneck Island that they get their water from. The green shaded regions are municipalities whose public water supply is strictly groundwater. So they pump their water out of the ground using wells. So they have strictly groundwater. And then the beige, yellowish, these water departments, their water supply is a mixture. So for example, Kent County, some of the water they supply their customers, they purchase from Providence Water from the Citrate Reservoir. So that's their surface water. They also have 2 large wells, which they pump groundwater out. And so the water they provide their customers is a mixture of surface water and groundwater. So you can see where you live in Rhode Island, and what sort of water your municipality provides you. Is it surface water, groundwater, or a combination of both? Now, I might be wondering, what about the people that live in the white, right? Where do they get their water from? Well, they have their own water. They have to have their own personal well or spring in which they are, and so they rely on groundwater. So they have their own personal well and spring. I grew up with my house having its own spring. So our water was provided to us. We didn't purchase our water from anyone. Our water was provided for us from the groundwater supply, which we had to test it ourselves and everything, make sure it was drinkable. And then as we'll learn, if there was a long period of time with no rain and the water table dropped too low, then our spring would run dry and we wouldn't have any water at all. So, those are risks that come with having your own water supply. But if you live in an area that doesn't have a municipal water supply, you have to have your own water supply. So groundwater is stored in subsurface space. Okay, we call this pore space. It's the empty space between grains of soil and sediment. It's also in loose unconsolidated sediment. There's also pore space in sedimentary rock. It's the empty space between the grains of sediment and the rock. And there's also a little bit of pore space in the cracks and joints in crystalline rock, like igneous and metamorphic rock, right? So, but by far the most pore space is in unconsolidated sediment, and then second is in sedimentary rock, and then there's very little in crystalline rock, like igneous and metamorphic rock. But that's where groundwater resides. It's in this empty subterranean space. So groundwater ultimately comes from precipitation. It falls on land and then soaks down beneath the surface and adds to the groundwater system. So that's where groundwater comes from. So features associated with subsurface water, we have different zones. The first is the zone of soil moisture. This is water that's held near the surface. So water molecules are polar, meaning that they have electrical charge, positive one end, negative on the other. And that causes them to be attracted to other water molecules and to surfaces. That's how if you throw beads of water at a wall, some of the beads will stick to the wall because it adheres to surfaces. And so a thin layer of water adheres to particles of in the soil, of sediment and organics in the soil. So this water, the thin layers held, film is held around these particles in the soil. This is called the zone of soil moisture. And this is the subsurface water that life requires to function. And so this is the water at the surface. This is the water that the root systems of vegetation take advantage of, the water that subterranean animals, worms, and so forth depend upon. So if you ever take a spade and you dig into the subsurface and turn over some soil, and you feel that dampness, that is the zone of soil moisture. You go beneath the surface, beneath the soil, you have what's called the unsaturated zone. So this is where if there is some soil down there, the sediment and the rock, there's water there, a thin film covering the grains and particles, just like in the zone of soil moisture. But the difference is that it's deeper beneath the surface. It's not right at the surface, right beneath the surface, and it's just this thin film again. So all the pore space is not filled up. It's not saturated. They're just a thin film. So this water isn't usable because you can't extract it because it's just a thin film surrounding the particles, as you can see here. If you go deeper, however, you reach the saturated zone. This is the region below the surface where the soil, sediment, and rock, all the pore space is completely saturated, completely filled with water. And it's this water that's in the zone of saturation that's known as groundwater. Now, this is the water that that can flow beneath the surface and that can be extracted from the surface. The water table, which you may have heard of before, is basically the upper limit of the zone of saturation. It is the boundary between the unsaturated zone and the zone of saturation, which is below the unsaturated zone. So to give you an idea, so here's the surface. Now, this is the unsaturated zone, and right here, and you see a little blow up of it where there's all this pore space, but the pore space is not completely filled with water. Down here, the blue, this is it's not actually blue, but just illustrated as blue. This is the saturated zone where all the pore space is completely filled in with water. And so this right here, the boundary between the unsaturated and saturated zone, this is the water table. So labeled this main water table. Okay, and so it's this water in here that's considered to be groundwater. So the depth of the water table can vary drastically. It can be anywhere from 0 to hundreds of meters deep. It varies seasonally because of precipitation varies seasonally. If you're in a period of time where there's been a lot of precipitation, the water table can increase. And if there's been very little precipitation, the water table can decrease. You cannot observe the water table directly, but you have to do so by mapping it using wells, which are holes you drill down to the ground. Now, sometimes there's been a lot of precipitation, basements can flood. This is because if we have a house, right, here's the surface and here's the basement. Basements aren't always built watertight, waterproof, because usually the water table is down beneath it. But if there's been a lot of rain, what happens is the water table, so there's more and more groundwater, so the water table is closer to the surface. And the actual water table is higher than the floor of the basement. So what happens is then water seeps out, this groundwater seeps out through the walls of your basement, and your basement will fill up with water until the height of the water table. And then once this groundwater is able to drain eventually away and it goes back down to its original height, then your basement will dry out, right? But as long as the water table is up here, you could pump this water out and water will keep on flowing into it, right? So that's how basements can flood. There's been a lot of rain, right? It's because the water table comes closer to the surface and actually rises above the depth of the basement. And if your basement walls are not watertight, water will seep in. So how we map the water table is, so we're looking at a map here, and each of these blue dots indicates the location of a well. What they drew, you drill a well. We drill a well. This is the water table. The well will fill up with water until the height of the water table. So if you know the elevation of the surface, and then you can measure the depth down to the water table, then you can calculate the elevation of the water table by taking the elevation of the surface minus the depth. Then you plot the elevation of the water table. This is all above sea level at the location of the well. So these numbers indicate the elevation of the water table. Then we draw these elevation contours, like on a topographic map, if you're familiar with the topographic map, where a line, a contour, or a line like this one labeled 150, it represents a constant line of elevation. And then you see how 140 is down here? That means that this is 140 feet above sea level. And so then anything over here is higher than 150, and everything on this side is lower than 150. Because we draw these contours to separate. You see how this right here is higher than 150, but everything down here is lower than 150. So we draw the 150 contour right there. Now we draw a line that separates everything that's 140 or above, and everything that's 140 and below. And that's the 140 contour, which you can see drawn right here. We do the same thing with 130 and 120, right? And then 110. And so we get these elevation contours. And you could see how the elevation decreases in this direction. And so this is the direction of steepest descent. So the water table actually slopes down in this direction. And so you know that water flows from high to low elevation. So if this is the surface and this is the water table, because it's higher elevation over here, water will flow, groundwater will flow from high to low elevation. So by mapping out the contours of the water table, that tells us which direction and also how fast, gives us some information on how fast groundwater will flow. And that's important to know, especially if the groundwater is contaminated, or if we're worried about it potentially becoming contaminated, because we don't want contaminated groundwater to, we want to know where it is, because people could be potentially relying on this for a drinking supply. Now, surface water can interact with groundwater. So a gaining stream is a stream channel in which gains water from the local groundwater system. And this occurs because the elevation of the water table surrounding the stream is higher than the elevation of the stream itself. And so because water flows from high to low elevation, groundwater will flow out of the ground into the stream. This is how some streams continue to flow long after periods of no precipitation. So for example, if this is the surface, this is a stream channel, and this is the water table. Because the water table over here to the left and right is higher than the elevation of the stream, water will keep on flowing into the stream channel. And so often these stream channels are ones that are in valleys. Where a losing stream is a stream that loses water because the water table is lower elevation. And so in that case, it's usually on a flat terrain. The water table is lower than the stream channel, so water in the stream channel will soak down to the ground and become part of the groundwater. And so these losing streams, they become dry in prolonged periods of no precipitation, and they only have water flowing through them after a precipitation event. So we find a lot of these losing stream channels in the western part of the country where it's more arid. So the water table is much lower beneath the surface, and it might be flatter. And so there's less topography to the water table. And so you can have these stream channels that are dry and they just have, flash flow through them after precipitation event. Where our stream channels here, because it's not arid and we have more topography, they tend to run more consistently. So it's very, very rarely that you find a stream bed in the Northeast that is dry. So here's an example of a gaining stream where the water table is higher elevation than the elevation of the stream channel, so water flows into it. This is a losing stream channel. It's connected, so it's still connected to the water table, but it's still losing water because the water table over here is lower than the stream channel. And this is a disconnected losing stream. So both of these are losing streams, they're losing water, but just one's connected and one's disconnected. So now we're looking at factors that influence the storage and movement of groundwater. So porosity is a measure of it's a percentage of the total volume of rock that is empty space or pore space that water can reside in. So basically porosity is a measure of how much water a material can hold. Remember, a pore space are all those countless voids or openings in soil, sediment, or bedrock. And the variations in porosity between materials can be significant. For example, sediment is usually very porous, unconsolidated sediment, like mud, sand, gravel, has porosity between 10 and 50%. Where sedimentary rock has a lower porosity, but it's the most porous of all the three types of rocks, all three types of bedrock, where igneous metamorphic rock have very little porosity, as you can imagine, right? They're crystalline rock where the crystals are intergrown, so there's no real pore space. So as far as porosity goes, unconsolidated sediment is the most porous. Then there's sedimentary rock, which is not as porous as unconsolidated sediment, but it's the most porous type of bedrock. And then you have igneous metamorphic rock, which have very little porosity. Then we have permeability. Permeability is the ability of a material to transmit water. So basically, it's how easily water can flow through the material. So in order to be permeable, first of all, the material has to be porous, so water can be present inside of it. But those pore spaces have to be large enough and connected that the water can flow through it. So you think of materials that are porous that we interact with. Well, clothing like cotton is porous, right? Water can pass through it. A coffee filter is porous. Sorry, cotton or clothing is permeable. Water can pass through it. Coffee filter is permeable. Sponge is permeable. Things that are impermeable, for example, rubber, plastics, and so forth, right? Because they have no pore space and water cannot pass through it. It is possible to be porous, but not very permeable. For example, clay. Clay has a high porosity. It can hold a great deal of water. That's why clay is actually heavy, pretty heavy, because it holds a lot of water. Water is heavy. And it's actually the water in the pore space of the clay that kind of gets in between the grains of sediment that allows them to move past each other easily. It reduces friction, which allows you to change the shape of clay. There's the water in there, the adhesive and cohesive properties of the water molecule. Remember, because water is a polar molecule, it helps hold it together. And so it's the porosity of clay, the really tiny sediment, grain-sized sediment with all that water in it, that allows you to mold it into different shapes and allows it to hold that shape. But the pore space is really small, so water has a really hard time moving through the pore space, giving it a low permeability, right? The water, if you put a hunk of clay on a piece of paper, the water just doesn't start seeping out of it. Water will slowly leave the clay, slowly evaporate, and it'll dry out. But if we want to speed it up, that process, that's why we put things that we make out of clay in kilns, which heat it to very high temperatures, which bake out all the water, cause all the water to evaporate out. And then all the minerals that were dissolved in water crystallize out and they cement the clay together in place. That's how you make pottery and so forth. So clay is an example of material that's porous. It can hold all water, but because that pore space is so small, water has a hard time moving through it, so it's fairly impermeable. And so clay is an example of a natural aquitard. An aquitard is an impermeable layer that hinders or prevents the movement of water. Clay is a good example. Other examples of aquitards include crystalline rock, like a layer of igneous rock, other igneous intrusions, metamorphic rock. Those are good examples of aquitards, layers that hinder the movement of water because they're impermeable. Where an aquifer is the opposite. It's a permeable layer of rock strata, or a layer of sediments that is able to transmit groundwater freely. So layers of unconsolidated sediment like sands and gravels are good examples, and sedimentary rocks like shales and sandstones and conglomerates are also good examples of aquifers. And so there's a lot of aquifers in the Northeast here and other parts of North America, mainly because of all the sediments that were deposited during the last ice age. For example, if you're familiar with the bottled water company Poland Springs, they get their water from spring water in Maine, which they're using all these aquifers that are sediments that were deposited by the glaciers. And we also have the same thing here in Rhode Island. Most of our aquifers here in Rhode Island are glacial deposits. So they're sands and gravels that were deposited by the glaciers. Now the sands and gravels are buried, but they're beneath the surface, right? But they're filled with water. All their pore space is filled with water, and they act almost as an underground reservoir that we can tap into and extract that water. Where if we had nothing but, igneous or metamorphic rock from the surface down, we would have no aquifers. We'd have very little surface water. Very little groundwater. So this is a simple groundwater flow system. We say that groundwater flows under the force of gravity from high elevation to low elevation. So there's precipitation falls, it soaks in, and it adds to the groundwater system. But that it flows from high to low elevation, and so here the groundwater system is being recharged by precipitation, and here groundwater is flowing out into this gaining stream channel, which is carrying it away. So groundwater is being discharged there. And so how we measure how groundwater will move, we already know that groundwater will flow from high to low elevation along the path of steepest descent. But how fast will it flow? Well, to determine this, we have to calculate the hydraulic gradient, which is basically the slope between 2 points. So if we want to know how fast groundwater will flow from point 1 to point 2, we need to know the horizontal distance between them, d, and the change in elevation between them, which is h1 minus h2. That gives us the hydraulic gradient. The larger the hydraulic gradient, the steeper the slope, the faster the water will flow. If h1 and h2 are the same height, then h1 minus h2 is 0. That means there's no hydraulic gradient and water will not flow. So you have the hydraulic gradient, but then you also have to take into consider what material it's moving through. So this is called the K factor, which is basically how permeable the material it is. The K factor of sand and gravel is really high because it's very permeable, where the K factor of, say, sandstone and shale is lower because the pore space is smaller because it's actual consolidated rock. All right, so you have to multiply the hydraulic gradient by the K factor, and that gives you the rate of flow of the groundwater. Right, and as I said, this is important because, let's say we have a reservoir, so surface water, that's being used for a public drinking supply. And let's say there's a road over here. There's a tanker truck that crashes, and the tank gets a crack and there's a leak. Now these chemicals are going to seep down into the groundwater. And now if we've mapped out the groundwater system, we know that groundwater is going to flow. It's flowing into this reservoir. So now these contaminations are on their way. So if we have this mapped out, we know what the hydraulic gradient is, we know what the K factor, we know, okay, how long do we have until this groundwater reaches that water supply? And that gives us a time frame as to how long we have to basically mitigate the situation or remediate it. And so the way they do that is they either they drill wells and they pump chemicals down there that would neutralize the toxin, or they drill wells and they start pumping groundwater out in hopes to pump out all of the toxins. So springs are the natural outflow of groundwater that were produced by the intersection of the water table with Earth's surface. So we know how outcrops are where bedrock intersects the Earth's surface. Well, a spring is nothing but an outcropping of the water table. And springs are often produced by aquitards that prevent the downward movement of water and create water to accumulate on top of them. And whenever that aquitard, that impermeable layer, outcrops to the surface, the groundwater that is accumulated on top of it also outcrops there and flows out of the ground. So that groundwater also obviously has to be in an aquifer, permeable layer above that aquitard. And so, for example, this is all an aquifer, right? This permeable layer, but there's this aquitard here. Maybe it's a deposit of clay. And what happens is this groundwater accumulates on top of it. And where this aquitard outcrops, this groundwater is outcropping too, and it's flowing out of the aquifer, out of the ground, creating the springs. That's why springs usually occur along a hillside, like this. So wells are what we drill whenever the water, groundwater doesn't come to the surface. We have to go down and get the groundwater. So a well is a hole that we bore down into the ground, down into the zone of saturation, where the groundwater is. What happens is, we drill this well, as illustrated before. If the water table is right here, the hole will fill up with water up to the height of the water table. So now this acts as a reservoir. Or if we put a pump down here, we can pump the water up out of the ground. If you've ever seen the movies, the old-fashioned hand pumps where they pump water, what they're doing is they're manually pumping water out of a well. Or the really old wells where they would have that stone wall built around it, and they'd have the bucket on the crank, and they'd crank the bucket down, and the bucket would fill up with water, it would go down, and it would collect water, and they'd crank it back up. That's how they get water out of the well. So whenever we extract water from a well, what happens is we create what's called drawdown. So if this is a well, this is the water table. And if we extract water at a rate where we keep the water level in the well right here, well, the water is going to flow out of the ground, keep on flowing out of the ground to replace this water, because this water is now higher. The water in the ground is higher than the water in the well. So eventually, the water table itself will be drawn down and connect with the height of the water that's maintained in the well. If we maintained a height in the well like this, the well would be drawn, the water table would be drawn down even more. So what this does is this creates a cone of depression. So if you'd rotate this drawdown 360 degrees, it's a cone that almost comes to a point around the well. And so the lower you keep the water level in the well, the more drawdown you create, and the larger the cone of depression. Now the cone of depression, it creates a larger hydraulic gradient, right? It's a steeper slope of the groundwater, so groundwater will flow in at a faster rate, right? But what happens is, if this cone of depression is large enough, it can cause nearby wells to actually run dry. For example, here are 2 domestic wells. You can see the drawdown that's produced from extraction of water, right? But this new large high capacity well is drilled, and they're extracting water at a much greater rate in order for irrigation. And it creates this large cone of depression, this large drawdown, so large that these wells are no longer, the water table is now below these wells. So these wells, these 2 smaller wells, they are now dry. So they're no longer productive. And so in order to make these wells productive again, they have to be drilled deeper, which costs money. And so there's, you can imagine the legal implications of this. If someone puts in a high capacity well, is pumping water out of it, and it causes this drawdown, they can compromise your water supply. And that's the thing, we realize that, well, this is my property, I have a well on my property, but what other people do elsewhere impacts you, because, groundwater and, the earth itself doesn't know property lines. It doesn't know, like, oh, this is a boundary. So what someone does at location A influences all the locations around it, right? So it's all interconnected. That's the same way if you're polluting the groundwater, right? If you pollute the groundwater at location A, it's polluting the groundwater at all locations around it. So if you're using well water or if you're using groundwater in general, it's important to know what's going on around you. So for example, we used, as I mentioned, spring water in the house I lived in growing up. And on the hill above us, the dairy farmer that lived on the road would lease that land and would grow corn for haylage to feed his dairy cows. And in the spring, in the early spring, before planting, he would always fertilize it by spraying liquid manure on the field. I remember asking my dad as a kid, it's like, Dad, I know that this water coming over spring is coming from the rain that's falling on those fields and soaking down to the ground. It's like, but it's flowing through that manure, right? So does that mean that, you know, the water we're drinking is contaminated by that? And my dad told me, oh, by the time the water gets to our spring, it's been long enough that it's been purified. And I was like, oh, okay. So, and we'll talk about that, the purification process. But it's important to keep in mind that if maybe there was a chemical being dumped on there, that might not have been the case. Our well could have been contaminated. So it's important to keep in mind what's going on around you if you are depending on groundwater. So an interesting feature that can form is an artesian well. Artesian well is a pressurized well. So you see this aquifer is sandwiched between two aquitards and it's at a slant. So what happens is the weight of the water up here pressurizes the water down here. So there's this pressure surface, which is equal to the highest elevation of the water in the aquifer. So if you drill a well down here, the water wants to come up will be pushed up to the pressure surface. If you drill a well here, the water won't come to the surface because the surface of the land is above the pressure surface. It will go up to the pressure surface. But if you drill a well here, because the pressure surface is above the actual land surface, the water will actually flow up out of the ground as an artesian well because it's pressurized. That's how these wells this water can flow up out of the ground. It's because it's connected to an aquifer that's on a slant, and so the water in the aquifer is pressurized. This is a similar concept to how we use groundwater for municipal water. So if the whole town was relying on groundwater, it'd be very inefficient if everyone had their own pump and their own well. Because every time you'd want to turn on your faucet, a pump would have to turn on, pump the water up out of the ground and come out of your faucet, out of your shower, into your toilet, whatever. So what a town does is they construct a water tank above the well. They have a large pump that pumps water up into the water tank. Because this water is at a higher elevation, its weight pressurizes the water in all the plumbing. So now when you turn on your faucet, the force of gravity pushes the water through and out your faucet. So if you'd so the higher you go, the less pressure there is. So if you build a building that's taller than a water tank, if you opened up a faucet up here, water would flow into the plumbing only up to this height. So you'd have no water. That's why tall buildings like in a city, they have to construct their own water tanks at the top of the building, pump water up into that water tank. So whenever they open up the faucets, the water will be pushed down in. But so that's why we have water tanks. It acts as a reservoir for groundwater we can pump up, and it also provides the pressure to pump the water through the plumbing. So there are several environmental problems associated with groundwater, and many of them are because groundwater, unlike running water, is out of sight. And so it's a little bit more risky, where you can see a polluted stream fairly easily, where it's hard to see polluted groundwater. One environmental issue that actually isn't related to pollution, but is related to the unsustainable withdrawal of groundwater is land subsidence. So remember that groundwater fills the pore space. It's the empty space in the aquifers. Now, if you extract that groundwater at a rate faster than it's replenished, then what happens is you remove the groundwater from that pore space before it's replaced. And that aquifer is buried underneath other layers of sediment.
And so there was a lot of pressure on it. And that water in that pore space was helping support that pressure. But once you remove that water from that pore space, faster than it's replenished, now that pore space then collapses under the weight above it. So thus reducing the porosity and permeability of the aquifer. And so now not only have you, by extracting water from that aquifer faster than it can be replenished, not only have you decreased the capacity of that aquifer, but also all that pore space collapsing causes the actual ground to sink down a little bit, subside a little bit. And there's been extensive agriculture and irrigation in the Central Valley of California. And so much groundwater has been used at such a fast rate that the valley has become even deeper from ground subsidence, because groundwater has been pumped out of these layers of these aquifers, these subterranean layers of sediment, faster than it can be replenished. And so this is where the elevation of the San Joaquin Valley was in 1925, 1955, here in 1977. So all this land subsidence, this was all space that was underground, pore space that was filled by water that was pumped out, and that space has collapsed. So now you got to go deeper to find groundwater, because if you go to deeper aquifers that haven't yet been collapsed. So land subsidence is a significant issue in places where the groundwater is heavily relied on. Then we have groundwater contamination. If you have well water, then you have to be really concerned about this. So most houses, if you live in a town, you have both municipal water, which water is provided from you from either groundwater, running water, or both. And then you also have a sewer system where your wastewater is piped, it's taken away, it's taken to a processing facility, a sewage treatment plant, where the wastewater is treated and then released back into the hydrosphere. All the harmful agents have been neutralized, at least the biological agents. However, if you don't have a sewage system, then you have a septic system. And a septic system is whenever your wastewater goes into a large tank. What happens is the solid waste settles to the bottom of the tank, and then the liquids are able to leach out the top of the tank. And they leach out into what's called a leach field, where pipes that are surrounded by gravel, pipes that have holes in them, and it's surrounded by gravel, carries the wastewater away from the tank and allows it to soak down into the ground. Now, the idea is this water is sewage water, right? It's harmful, has a lot of biological agents in it. But the idea is you can have a well, right, of a neighbor next door, but it'll be fine even though there's a septic tank next door, because if the permeability of the subsurface is low enough, that contaminated water takes months to years to travel to that well. And by that time, all the microbes, all the biological agents have died because they've ran out of food or in hospitable conditions, so they're died. So the water, all the biological agents are neutralized. However, if the subsurface is too permeable, where the water flows too quickly, it can make it to that well before it's purified, and then you have contaminated drinking water. Now that's only for biological agents. If you dump chemical agents like acetone or oils or other bleach, other chemical agents, those don't necessarily break down. It's those chemical agents will find their way to this well, just a matter of time. So that's why you should never dump harmful chemicals down your drain, even if you have a sewage system plant, even if you have your town has a sewer, because the sewage treatment plants, they treat the human waste and the soaps and stuff that they expect to find in the drainage water. They don't expect to find stuff, harmful chemicals. They don't treat it. So you shouldn't really dump stuff like Drano down your drains. You should snake your drains, because those chemicals, they're going into the hydrosphere. And to give you an example, so a lot of the suburban neighborhoods that have septic systems, they're finding that in the wetlands around these suburban neighborhoods, the fish and the amphibians were
having a high rate of the occurrence of hermaphrodites, which hermaphrodites are organisms that have both male and female gonads. So they have testes and ovaries. And ovaries. And so the reason is because fish and amphibians, they don't have impermeable skin like reptiles and mammals and birds do. Their skin isn't watertight. And so whatever's in the water is absorbed into their bodies. Now, we don't think about it, but everything we put into our body, it'll eventually pass through our body and come out with our waste. That includes pharmaceuticals, so blood pressure medication, any sort of medication we ingest, some of it we pass it, and that includes any hormonal, any hormones put in our body. So a common hormone used is the birth control pill, and so birth control pill is taken by a lot of women, and then those hormones make it into the wastewater. And then all of the wastewater seeps out of these septic tanks and into the groundwater, which then makes its way into the wetlands. And all those hormones, estrogen or progesterone, I forget which one's in, I think it's both, it depends on the part of the cycle of the birth control pill. But those hormones now interrupt the development of the fish and the amphibians, resulting in hermaphrodites. And so they realized that that was the cause of it, right? It was all the birth control, all the hormones for birth control in the wastewater that was seeping into the wetlands. So, you know, that's a great example. Is something that we think is isolated, like you flush your toilet. You don't realize it, but what you flush down your toilet, what you pour down your drain, is going to make it into the bay. It's going to make it into the local pond. It's going to make it into the local swamp. Everything is connected. You know, it is an earth system. Nothing is isolated. And it's a hard thing to wrap your mind around sometimes, but it's the truth, and it's important to keep that in mind. So one of the things, whenever you build a house, they have to do a perk test, which if you need to put in a sewer system where they drill a hole down into the, basically they drill a well, and they see how long it takes that well to fill up with water. If it fills up with water really quickly, that means the subsurface has a really high permeability, and you have to take extra measures if you're going to put a septic system in. But if it takes a long time for it to fill up, I mean, there's a low permeability, which means it's safe to put in a septic system. Other sources of groundwater contamination are anything we put on the ground, right? Pesticides. Imagine we spray pesticides on farm fields. Well, when it rains, those pesticides and herbicides, they get added to the groundwater system. You might have heard of a chemical called DDT, which years ago, DDT was a very common pesticide. It was sprayed on farm fields, but they noticed that fish, if they were finding dead fish in streams, dead amphibians, and dead birds at an alarming rate. And upon looking at these, doing autopsies on these dead organisms and looking at their toxicology, they are finding DDT. They were being killed by the pesticide. So what happened is the DDT went into the groundwater system, and then it was flowing into the streams. And so the fish were being poisoned by the DDT in the streams, so the amphibians. Then the birds that were eating the fish were being poisoned by the poisoned fish, and they are dying too. So just spraying those chemicals on the fields caused it to begin to just seep all through the ecosystem. It just been spread all through the ecosystem. So once again, everything is connected. Landfills, dumping this waste into large holes in the ground, if they're not properly lined with aquitards, and those aquitards aren't properly maintained, then all that harmful water that from rainwater that flows through these landfills will enter the groundwater system, which can cause a lot of harm. And so also mine drainage, so groundwater that is flowing out of mines, abandoned mines, it's leaving the ground faster than it normally would. So minerals that are dissolved in the water come out at a much higher rate. And so you get this really hard water that has a lot of iron or sulfur dissolved in it. And so you get these red or orange streams, like you see in the bottom right here. Now this water is so hard that it can't support life. And so I grew up in Pennsylvania. There's a lot of old coal mines, and so seeing streams like this was fairly normal. And it's very sad because these are dead streams from the mine drainage because the water is so hard. They're completely bereft of life. So it's completely ruined. And so it's very easy to not notice the contamination of groundwater. So it's something to keep in mind of. And if you ever go to next time you go to a gas station, if you look at the cement floor around the gas station, you'll see like there's these lids where they fill up the tanks underground. They're called USTs, underground storage tanks. That's where the gasoline's held and it's pumped out of. But you also see these smaller caps, and you'll see they're called well access or test wells. And so every now and then, whatever the environmental agency, so in the case of Rhode Island DEM, they go around and they use those are little tiny wells. Those are monitoring wells, and they extract samples of the groundwater from those wells and they test it, because that's how they monitor if the USTs, the underground storage tanks, have been compromised, if they've corroded and have a crack in them, and the fuel is leaking out into the groundwater. So you have to constantly monitor that to see if there is a leak. Because if not, then you can have these fuels and stuff leaking into the groundwater, and it would be unknown to people, and it could cause harm. The example of this, a very devastating example, is the Love Canal disaster. There was this chemical company known as the Hooker Chemical Company in upstate New York that produced in their industrial process this toxic industrial waste. Now they bought this canal. So this canal was used for economic use, for shipping goods. Then it was shut down, and then it was used for recreational use. So they'd have like gondola rides along this canal. That's how it got its name, the Love Canal. But then this chemical company bought the canal. They lined it with layers of clay as an aquitards. So they took the proper precautions, and they were dumping the waste in it. All right, so it wouldn't seep into the water table. Now, later on, the property around the canal was later bought up by developers, because this is outside Niagara Falls, and Niagara Falls was growing as a town, and so developers wanted to build a school. Because to build a suburb, what you need is you basically need a school to serve the children in the suburb, and then you develop the property around it, build houses, and you sell those houses. So this was bought, and in the chemical company's defense, they really did not want to sell this property that this canal is on, because they knew it was a liability. So to the best of my recollection, after a lot of legal he and hawing, I think it was eventually sold, I think for $1, with documentation absolving the chemical company of all liability. Well, so all the safety precautions were taken in that transfer of the property from the chemical company to the developers. But then the developers, as the property is sold off, was divvied up and sold off, if proper safety precautions weren't taken, and the information, knowledge that dump site was there was not necessarily known. And as the area was developed and construction companies were building houses and so forth, the aquitards were breached, unfortunately. And because aquitards were breached, all those chemical toxins were seeping into the groundwater underneath all of these houses. And it was poisoning all the people that lived in these communities around this dump site. And it caused, and then because the aquitards were not maintained, they dried out and cracked and resulted in further contamination. So many health problems were reported in the area, including increased miscarriage rates, birth defects, increased increase in cancer rates, an increase in mental retardation, and then other developmental disabilities. And so this is all due to the poisoning of the groundwater. Now, this was prior to the 1970s. And in the 1970s, it's events like the Love Canal disaster and seeing all the contaminated running water and groundwater that the federal government, there was enough public outcry that the federal government in the 1970s created a new government agency called the Environmental Protection Agency, the EPA. It was created under the Nixon administration. And it's from the creation of the EPA that things like this, the Love Canal disaster, don't happen anymore. So, you know, if you ever hear like government regulation, a lot of it exists for a reason. Unrestricted capitalism results in things like this Love Canal disaster, right? Where there's not some body, governmental body, overseeing, making sure all the safety precautions are taken. Now, whenever you purchase a piece of real estate, there are different schedules or different documents that have to disclose any dump sites in the area. And that part of that is because of this Love Canal disaster. All right, so anyone who purchases real estate is in the know of any potential hazardous dump sites within a certain radius of the property. So it is important that we have some regulation, right? Because if not, then people suffer because, you know, it's not always in a company's best interest, or not, I shouldn't say best interest, and financial best interest to take their correct or proper environmental steps or procedures. You know, fortunately, nowadays, companies are switching more to the triple bottom line stance, where they not only look at their financial bottom line, but their impact of all the stakeholders involved, not just the stockholders, and also the environment. And so they take into account the true cost of all their actions. And so they have a much a better approach to how they interact with the people around them and the environment around them. But that's not always the case. And so we do need agencies like the EPA and certain governmental regulations to keep the public safe, because we all share the environment. So hot springs and geysers are another feature of groundwater. So when groundwater circulates at large depths beneath the surface, it is warmed because we know temperature increases with depth, especially if there's magma intrusions beneath the surface that will heat the groundwater. And so warm water more easily dissolves minerals, subterranean minerals. And whenever that warm water reaches the surface, it cools. When that warm water reaches the surface, it forms a hot spring because the water is obviously hot. Whenever it cools, those dissolved minerals, they precipitate out, forming chemical sedimentary rocks. So this is Mammoth Hot Springs in Yellowstone. You can see the water is cascading over these deposits of chemical sedimentary rocks that have been deposited as the minerals precipitate out of the water. Now, geysers form whenever there's a cavern, which we'll learn, or empty spaces beneath the surface. The cavern fills up with water. And then there's a heat source, maybe a nearby igneous intrusion that heats up this water. But because it's underneath the ground, this water is pressurized. And so the water has to be heated above the boiling point before any steam starts to form. Whenever some steam starts to form, the water takes up more space as a vapor than it does a liquid. And so it expands and it pushes some of the water out to this inertial burping out of the water. Whenever that water is burped out, it reduces the pressure in the rest of the water. And that reduction of pressure allows the rest of the water to vaporize very quickly. And whenever that water vaporizes very quickly, the pressure increases because it takes up more space as a gas than as a liquid. That increased pressure, due to the rapid vaporization of all the water, causes the water vapor and the remaining water to be ejected out of the out of the geyser. So that's why a geyser erupts. And that's why a geyser erupts with a certain periodicity, because it takes a certain amount of time for the cavern to fill up with water, for the water to be heated to the point where it begins to boil, and then for it to be ejected out. Right, so like Old Faithful erupts with a certain periodicity because this cycle takes a certain amount of time, depending on the size of the cavern, the rate of heat flow into the water, and so forth. So groundwater can do a significant amount of geologic work. It can form caverns, which are vacant or void spaces beneath the surface. And this is because groundwater has small amounts of acid in it. So as water falls as precipitation, it absorbs carbon dioxide and sulfur dioxide, which create acids like carbonic acid and sulfuric acid. Whenever they dissolve into the groundwater, the slightly acidic water easily dissolves subterranean rock, especially calcite rock like limestone. And as that limestone is dissolved and carried away, a void is left, forming a cavern. You can see a picture of cavern form here. And then water seeps out of the ceilings, and as that water seeps out, dissolved calcite precipitates out, forming these stalactites, kind of like how an icicle forms. As water flows over the icicle, a thin layer of ice freezes onto the outside edge of the icicle. And so as layers and layers are added, the icicle grows in thickness and length. That's the same way a stalactite forms. And you know they're stalactites because they hold tight to the ceiling. Whenever the water drops off the end of the stalactite, it hits the floor, where more calcite precipitates out, and it accumulates, forming these structures that grow up from the floor. Those are called stalagmites. Whenever a stalactite meets a stalagmite, it forms a column. Now, if you ever go into a cavern, which you have the opportunity to, I strongly encourage it, you're not allowed to touch the stalactites or stalagmites, because if you touch it, the oils of your skin get deposited, and then the water doesn't flow over that oil. And so no minerals will be deposited where you touched it, and it'll cause the continued formation of the stalactite or stalagmite to be disrupted. So whenever a landscape has been significantly altered by groundwater, that forms what's called karst topography. So here we have limestone bedrock, and here's the water table. And because it's limestone, groundwater easily dissolves it and creates these caverns. And also the stream easily dissolves the groundwater, and it creates this large bedrock stream channel. Now the caverns, what happens is sometimes their ceiling collapses and it forms what are called sinkholes. And these streams can then flow into the sinkholes and become part of the groundwater system. And then water can flow out as springs. So this topography is karst topography. It's shaped by the subterranean weathering, chemical weathering of the rock by groundwater. And so sinkholes are a very common feature of karst topography. So here you can see these sinkholes. The ceilings of these caverns have gradually slumped down, forming these gradually sloping sinkholes, where sometimes it's a sudden collapse. So this cavern was unfortunately beneath a house, and the roof of it collapsed in, and the house collapsed into it. Interesting thing is, you can see there's a moving truck right here, right? These people are moving out because of the inherent risk. This is a video. I'm not sure the hyperlink works, but it's a sinkhole in Louisiana. You can see this is a large sinkhole. The water table is actually above the surface. So anytime the water table is above the surface, that's how you have wetlands or marshes or swamps. That's because the water table is above the surface, there's always water above the surface. But you see, this is the edge, and these trees, when it breaks down, these trees are sink down into the sinkhole. Find out on YouTube, it's interesting to watch. Here, this sinkhole formed, and this half of the house is fallen into it. This is an old sinkhole. You can see it's so old that trees are growing up from the bottom of it. There's one formed in China. China has a lot of limestone, so has a lot of karst topography. And so these sinking streams, these streams just disappear into these caverns, become part of the groundwater, and then these springs where water just flows out from the ground. So this is a map where we have karst topography in the United States. So the green is carbonate rock, like limestone. So the dark green is where it's exposed, it's right at the surface. The light green is where it's buried under other sediments. And so in Florida, we have a lot of limestone, so we have a lot of karst topography. In Kentucky, Indiana, Ohio, Missouri, and out there, we have a lot of karst topography too. If you look into or Google the Corvette Museum in Kentucky, the Corvette Museum actually collapsed into a cavern, a sinkhole formed, and all the Corvettes fell down into the sinkhole. It's pretty interesting. And so one of the most extreme forms of karst topography is now where almost all of the layer of limestone is removed, except some sections of the limestone remained. You can see how below the limestone is a layer of shale. And so there's this flat surface that's produced because the limestones were removed, but the shell isn't as easily dissolved. But these towers of limestone that have been left remain. Some of them even have caverns inside them. So it creates this topography where there's just these towers of limestone extending up from the surface because all the limestone around them has been weathered and removed away. So here you can see that flat surface, right? The less soluble layer of rock beneath it, like shale or sandstone. Then this was all limestone. But the limestone has been all chemically weathered and removed, except these towers have remained. So it creates this really dramatic landscape, this tower karst. This is in China. Just you can imagine these towers of limestone that have potentially these caverns inside of them. Just to me, it seems like the set or the setting of an Indiana Jones movie or something. Then here's some more on a much smaller scale, some tower karst. You see these towers of limestone extending out as the limestone around them has been weathered away. That concludes our lecture on groundwater.